Let's look at another example. We want to ask whether the set of positive odd integers is closed under our four basic operations. So let's start with addition. Let's just try some examples with this set, adding two of the numbers together. How about we just add the simplest possibility we can think of, 1 plus 1. We get 2. 2 is not odd. It's an even number, so it's not within our set, and we can immediately say no. How about subtraction? Very similarly, just take any example you like. 7 minus 1. You get 6. That's an even integer. There's a counterexample. You could even use 1 minus 1 again. I like to come up with the simplest examples that I can possibly dream up. How about multiplication? Okay, let's try a few examples again. 1 times 1, well, that's 1. 1 is in our set. 1 times 3, that's 3. 3 is in our set. 3 times 5, that's 15. 15 is in our set. That is an odd positive integer. It seems like all the possibilities that I'm coming up with are indeed back in our set. Let's try to prove that it's always the case that we land back in our set. So what I'm going to do is dig my hand into the set and pull out two random numbers within that set. So I'm going to write 2a plus 1. Actually, the set said 2n minus 1. It doesn't really matter if you call it 2a plus 1 or 2a minus 1. Either way, you're going to represent an odd integer. The only difference between doing the plus 1 and the minus 1 is, in our case, the a and the b that we're picking can actually be 0. In this set here, the n has to be 1 or bigger. But the a and the b that I picked are either 0, 1, 2, or any integer bigger than that. Now I'm going to try to decide if I'm closed under multiplication by taking the two numbers that I just came up with, 2a plus 1, and multiply by 2b plus 1. Let's remember brackets because it's all of that multiplied by all of that. And if I do the multiplication, if I expand this out, I have to multiply the 2a by the 2b, and the 2a gets multiplied by the 1 gets multiplied by the 2b, and the 1 gets multiplied by the 1. So let's do that process. I get 2a times 2b. I get 2a times 1. And I get 1 times 2b. And then finally 1 times 1. I would like to try to show that this number is within my set. What I'd like to do to show that it's within my set is to try to write this in the format of 2 times some number plus 1. Every number in my set looks like this, where the something that I'm writing in the brackets here, something has to go there. That something has to be a number like 0 or 1 or 2 or anything bigger that's an integer. Now if we look from the step above, 2a, 2b plus 2a plus 2b, we can actually factor out a 2 from that expression. The first three terms above here have a 2 in common in each of those terms. So we can rewrite this as 2 multiplied by all of 2ab plus A plus B. Now what we just wrote does represent an integer that is either 0, 1, 2, or anything bigger. Remember, the A or the B could have been 0, 1, or 2, or anything bigger. So when we look at what's inside of the brackets here, the smallest case would be A and B are both equal to 0. Then you would add 0 plus 0 plus 0. And if A and B are any integer bigger than that, you'll get an integer bigger than 0, which is perfectly fine because it tells us that the whole thing will be 2 times an integer plus 1. And what we want is to conclude that it is indeed a set of the odd positive integers. So this is a capital O, not a 0. So the answer to this question is yes. Is our set O closed under division? Let's try to combine some odd positive integers again. Now, with division, it can be kind of tricky to make a closed set if you just have integers, because division allows us to make fractions. And we don't have any fractions in our set, right? If we look above at our set, there's no fractions in this set. It's just 1, 3, 5, 7, 9, 11. So let's go back to our question on division, and we can easily come up with a fraction like 1/3 is not within our set. So the answer to the question is no.